Hello, this is our first lecture for elementary stats for the social sciences, statistics 1. To refresh your memory, I am Dr. Jennifer Moses and I am your instructor. And this is just going to be a short lecture introducing you to the core mathematical concepts that I already assume you have walking into this class. And all the and this isn't a math class, not a math class, but we do use some mathematical tools in here. So it's going to be important to make sure that you're as refreshed as you can be on the mathematical tools that I assume you're walking in here with. And we're going to go through today is a number of mathematical equations that I don't expect you to be able to look at and then automatically solve like that, but they should feel really familiar to you. And with a little bit of sort of dusting off the cobwebs in your brain, I assume you could figure out how to solve them. Not because we're going to do math problems like this all semester, because in fact we won't be doing math problems like this all semester. Rather, these are the mathematical tools I assume you have walking in. And I want to make sure that you have them under your belt already, because this is a concept class and you can't learn some of the challenging concepts that we'll go over in this class at the same time as a bunch of new math, right? So I have to make sure that you have the sort of the required background mathematical knowledge. So let's go through what I assume you have walking into the class. So order of operations, percents, percentages, and ratios, summation notation, which is actually the only thing I don't assume you have, and I'll be teaching you that today, squaring, taking square roots, and solving basic algebraic symbolic equations. And here's a couple of links for you right here. davidlane.com as well as stuartcalculus.com that might be able to give you some refreshers on the mathematical concepts if you need them. So, order of operations. Please excuse my dear Aunt Sally. Order of operations, to refresh your memory, is essentially when you have a mathematical equation, an algebraic equation, and you're supposed to solve for x or solve for y or solve for any sort of unknown, this is the order that you're supposed to attack the equation with. First, you start with the innermost parentheses, and in equations, you always work from in to out, and unless otherwise stated, from left to right. So first of all, you have parentheses. Start with the innermost parentheses and work your way out. And then comes exponents. It's second. Then multiplication and division. They're actually the exact same mathematical operation. If you remember from multiplying fractions, if you're ever having to divide fractions, you just flip the second one over, and then you can just multiply. And it's the same thing. If you're multiplying, multiplication and division are essentially the same thing. Just like if you're multiplying 2 times 2, you could conceivably take 2 and divide it by 1/2, and you'd end up with the same thing, 4, right? Multiplication and division are the same mathematical operation, so they actually come at the same place in a mathematical sequence when we're trying to attack an algebraic equation. And then last comes addition and subtraction, right? And they are in fact also the same mathematical operation. If you, when you subtract, you can also think of that as adding a negative. Or if you're adding a negative number, you can also think of that as subtracting. It's essentially how far away are you from the original value, adding or subtracting. So moving on to slide 4. Here we have the first equation is absolute value, right? And how would I solve this equation? I already have the answer for you, but let's see if we can. So let me just show you how I would solve this equation and walk you through it. So the 8 becomes, because it's an absolute value, 8 becomes a positive 8, right? And then I'm adding 3, and 8 plus 3 is 11, right? That's the idea. The next one is subtracting a negative, right? And you can put the negative number in parentheses just so there's no confusion that this is a standalone negative number. And so to solve this one, it's the same idea, right? Because you're subtracting a negative number, you can say it's like you're subtracting debt. If you have $14 and you owe me $4, but I'm going to subtract that debt, right? Then I'm going to say no. You do not owe me those $4. In fact, here's those $4 back. We're good to go. It's really like you're subtracting the debt. So then you have $18, right? So you take 14, and since you're subtracting a negative number, it's really like you're adding it to get 18, right? Right. And here's multiplication. Hopefully you recall that anytime you multiply two negative numbers together, you end up with a positive number. So negative 2 times positive times negative 9 is just 18, much as positive 2 times positive 9 would be 18. And then the next one, 1/2 divided by 4. All right, and for this last one, we have 1/2 divided by 4. And how I would solve this one is I would just take I would keep it as fractions. And I would do 1/2 divided by 4/1. And as you probably remember, one-half divided by 4/1 is the same thing as 1/2 times 1/4, which is 1/8. All right, moving on to the next problem. So here we have exponents, squaring. To refresh your memory, whenever you're squaring, it's like you're taking the number and you're multiplying it by itself. So -6 squared is just -6 times -6. And we know that 6 times 6 is 36, or we could plug it into a calculator. To get 6 times 6 is -6 times -6 is 36. And we just to point this out, we know that two negative numbers is always going to be a positive. And because squaring is taking a number and multiplying it by itself, you're either taking a positive number and multiplying by another positive number to get a positive number, or taking a negative number and multiplying it by a negative number to get, again, a positive number. So squares are always positive, and that becomes sort of an important thing to think of as we go through the class, because this class deals a lot with squaring. We square and square and square. There's even a basic term in this class called a sum of squares, where you add up a bunch of squares. So remembering that a square is always positive is useful. So the next one here, we have a multi, so I'm looking at this one right here, right? Whoops. I'm looking at this one here, right? This is the one I'm looking at right now. This one right here. So how do I attack a problem like this, right? How do I attack a problem like this? Well, I'm going to start with parentheses, because don't forget, please excuse my dear Aunt Sally. I'm going to start with the innermost parentheses, and so I'm doing 5 plus 8/2. And because 8/2 is division, I'm going to do that one first. So let me solve it over here, right? So I'm going to have, first I'm going to solve 8/2. So I end up with 5, and then 8/2 is 8 divided by 2, so 4. So I end up with 5 plus, whoops. I end up with 5 plus 4, right? And so now I have 5 plus 4, and so the innermost parentheses ends up being 9. So let's rewrite that equation now that I've solved that aspect of this equation. Whoops. So I've now solved the innermost parentheses, following order of operations. And I have my outermost parenthesis, 65 minus 2. And then here I have 9. And then I have this parentheses, And then I have to complete this other parentheses, right? And then the last thing is a square out here, right? So now what do I do? Well, I still have a little parentheses here, but more importantly, this is 65 minus 2 times 9. Order of operations, multiplication comes before addition. So I'm going to take 2 times 9. 2 times 9 is 18. So now my equation is 65 minus 18 squared, right? Right? So now that's what I've solved. So now what is 65 minus 18? Well, 65 minus 20 is 45, but I'm not going to do it quite that much, so the answer is 47. 65 minus 18 is 47. Now, of course, you could plug that into a calculator. 65 minus 18 is 47. So now I have So now I have 47 squared. And what do you want to bet 47 squared is? 2,209. It is. You can go ahead and get out a calculator and check it. I guess that's a general comment about this class in general. You should always have a calculator with you as you're watching these lectures, and as I'm going through the examples, make sure that all the steps that I'm doing, you can do those steps too, and then when you're plugging in these basic arithmetic expressions, these basic arithmetic problems into a calculator, that you're getting the same number as me. Just so that you're confident that you could solve the same questions that I could. Now, this equation that we just went through, as I mentioned, we're not going to do a million different equations like this, but this sort of complicated expression, so if you can solve it, knowing to first do 8 divided by 2, then to add 5 plus 4, then to take 2 and multiply it by 9, then to know to take 65 minus 18, then to know to take 47 and square it. Knowing the order of operations is going to give you, making sure those mathematical skills aren't rusty is going to really, really help you succeed in this class. All right, so moving on. So now we're on this problem right here. So here we have x equals -3 and y equals +2. And this becomes important because this is sort of making sure you can recognize that symbols represent numbers. All the equations in this class, at least most of them, are expressed in symbols. Very few numbers in them. A few numbers, but mostly they're symbols. They're symbols that represent specific numbers. For example, we're going to learn in our next lecture that there's a symbol that represents the average. You know, an average where you take a bunch of numbers and you add them up and then you divide by the total number of numbers, right? If you wanted to know the average number of children in this class, you would take everybody's children. I have 1, you may have 0, you may have 1, 2, or 3, 4, however many. We would add up everyone's kids and to get, like, let's say our class has 12 children in it total. When you add up everyone's children, and you would divide by the number of people in the class, and then you would get an average number of kids in class. Well, there's a symbol that represents the average in any particular group of people. And many of the equations we're going to deal with this semester use that symbol. So it's important that you have that background mathematical knowledge of being able to apply symbols to mathematical numbers. So for example, x takes on the numerical value of -3. Y takes on the numerical value of 2. So then if I say, what is x squared times y squared, you can say, well, I remember that, or I can see here right on the page, that x is -3. Well, order of operations says exponents come first, so I have to take -3 and I have to square it. -3 squared is 9. Then I say, okay, well, y is 2, but order of operations says I have to take the exponent 3 of 2. And so you take 2 times 2 times 2. 2 times 2 times 2 is 8 because 2 times 2 is 4. 4 times 2 is 8. So you end up with 9 times 8 is, that's right, it's 72. Right? Right. All right, next problem. This is just basic percentages and being able to deal with percentages as well as proportions and ratios. So here we have 60% of 400. And how would I solve that? Well, the easiest way to solve a problem like this is to turn that percentage into something called a proportion. Now, to refresh your memory, a percentage is always out of 100, where 0% is none of it, and 100%, 100, right? 0%, whoops. Where 0% is nobody, right? If I say 0% of the people in this class, let's see, live in the ocean and breathe water, right? That would be accurate. 0% of us do this, right? Versus 100, so that number is 0. Versus 100%, 1, 0, 0. 100% of the people in this class have DNA, right? Notice that that percentage is out of whole numbers that range from 0 to 100. So a percentage is from 0 to 100. A proportion, on the other hand, ranges from 0 to 1. And so we're dealing with decimals now. So a proportion is going to range where 0.0 means none of it. So I could say there is a proportion of 0.00, proportion of the class that lives underwater and breathes water, right? All the way up to the proportion of 1. 1.00. I'm not a super fan of my stylus. I think I'm going to try to get a new stylus before our next video. But bear with me for this first video. All right. So a proportion, if let's say nobody in class breathes water, then the proportion would be 0.00, right? All the way up to a proportion of 1.00. 1.00 proportion of the class has DNA, right? We all have DNA. So just keep, so why do I point this out? Well, I point this out because it's important to keep track of the difference between percentages and proportions. We often talk in percentages, like every day, like there's a 50% chance that someone in the class is a woman, or there is a 70% chance of rain, or a 5% chance of this. We talk in terms of percentages, right? But in statistics, and in data analysis, which is what this class is all about, we can talk in terms of percentages, but much more often we're working with proportions where we're talking in decimals from 0 to 1. And so being able to tell the difference and know the difference between those two important concepts, because they're not the same, 0 to 100%, although is related to, it's distinct from saying from 0 to 1 in terms of a proportion. So how I would solve this problem, 60% of 400, how I would solve it is to turn that 60% into a proportion, and then I would multiply. I would take 400 and I would multiply it by 0.6. See how that's a decimal? I would multiply it by 0.6, plug that into a calculator, and that would return 240. There are other ways to solve this problem, but those aren't ways that are central to the concepts in this class. So keep in mind that anytime you want to turn a percentage into a proportion, all you have to do So here's my percentage. If I want to turn it into a proportion, I simply, because here, this is a whole number, right? 60. I start with the decimal point here, and I go 1, 2. I move it over 2 places. Now it's not a percentage anymore. It's a proportion. It's a proportion of 0.60. Proportion of 0.60. Always move it over 2 places, right? Let's do one more. So 60% is the proportion of 0.6. But let's say I have 5%. So here I have 5%, right? If I want to turn it into a proportion, I start here and I move the decimal place over 2 places. Well, so then what goes here? A 0, because I'm moving it over 2 places, right? So if you have a percentage of 5%, that becomes the proportion of 0.05. %5 is the proportion of 0.05. Now again, I assume you have this background mathematical knowledge. I'm just trying to dust off your brains, right? Right. All right. So next one. You need to know rounding rules, what it means to round. You round up sometimes, you round down sometimes, and what does that mean, right? Rounding never, ever, ever means you just chop off the last few numbers. There are rules to rounding, right? I'm not going to look at 7.2557 and say I'm rounding it to 7.25 because I'm just chopping it off. There is a correct way to round and an incorrect way to round. But anytime you have fewer numbers than you did before, that is called rounding, right? And so you either have to know whether or not to round that last number up or round that last number down. 7.2557, this first one here, 7.2557, that is 4 places after the decimal point, right? So let's say I ask you to round it to 3 places. What I'm telling you is I want you to give me a number that has only 3 numbers after the decimal point. And there's a correct way of doing that and an incorrect way of doing that, right? So the way I approach this is if I have 4 numbers and I only want 3 numbers, I look at the size of the 4th number. In this case, it's 7. And because 7 is 5 or above, I'm going to take that 5 and round it to 6. So because you round up, anything that's 5, you round up. Anything below 5, you round down. So rounding 7.2557 to 3 places becomes 7.256. 7.255 would just be wrong. It would just be wrong, right? You're rounding up. You're making this number slightly bigger. Let's say I'm rounding it to 3 places. What I do is I look at that, let's say I'm rounding it to 2 places. Well, then I ignore the 4th number altogether and I look at the 3rd number. And because the 3rd number is a 5, once again, I'm going to round up. That 2nd number is going to become a 6, right? That's how you round. Same thing with this next one, 16.071. If I want to run it to 2 places, right, this is what I'm doing now. If I want to run it to 2 places, I look at this 7. I go, oh, this 7 is above, excuse me, not that 7. My bad. I got ahead of myself. I look at this 4th number and I see that that 4th number is a 1. Now that 1 is below 5. And so I can just round down and leave it as 16.097, something slightly smaller than 16.0971. Now, if I wanted to round it to 2 places, then I would ignore the 4th number and simply look at the 3rd number. In this case, the 3rd number is 7. And because that 3rd number 7 is above 5, I take that 9 and I round it up to 10, or in this case, 16.10. So know your rounding rules, because we're going to be rounding a lot in here. Same thing with this last one, 34.8422. If I want to round it to 3 places, I look at the 4th number, which is a 2, and so it becomes 34.842. If I want to round it to 2 places, I look at the 3rd number, which also happens to be a 2, and I round 34.8422. 2 rounds down, so 34.84. All right. So now we get into real symbolic representation, or how to figure out how to manipulate algebraic equations that really have no numbers. They only have symbols. And so we need to know our exponent rules. We need to know about distribution rules, so that we can approach the algebraic equations in our class. So here we have 7 to the 3rd in the inner parenthesis. I'm working on this one. I have 7 to the 3rd in the inner parenthesis, but then on the outside of that parenthesis here, I have another z. It's essentially saying take z to the 3rd and then multiply by another z. Well, that just means z to the 4th, right? Right. Here we have in the second problem, here we have 2 numbers in parentheses with the exponent on the outside. And we know that we can, and this is some division happening here, right? And we know we can distribute that exponent, that c divided by d in parentheses to the 4th. We know that we can distribute that, exponent to both c and d and get rid of the parentheses. All right, what do we have here in the 3rd one? Working with that one now. If I'm going to get rid of the parentheses, what do I need to do? Well, I recognize that y plus x are in the parentheses. So if I had numbers, I would be doing them first, right? If these were numbers, first I would be adding, and then I would take z minus this whole big number, right? But if I don't have numbers, then the rule that I can remember is that when I have parentheses here, I distribute out this minus sign, right? I can distribute out the minus sign. Whoops, sorry, we went back in time. Weirdly. I go back in time. There we go. Now, what do I mean by distribute out the negative sign? Well, I have z minus y. Well, then this minus turns y into a negative number. Z minus y. And it also turns this x into a negative number. And so z also minus x. And it was z minus y minus x. Z minus y minus x. Right? Let's see. Whoops. Got z minus y, z minus y minus x. Make sense? I certainly hope so. All right, so the same thing here. First of all, so how do I approach a problem like this, right? Well, first thing I'm going to do is order of operations. I have to deal with anything inside the parentheses first, but I don't have any actual numbers here. So then I go, okay, is there any multiplication happening here? And indeed there is. Essentially right here, this x, right? This x right here has to get multiplied by y and multiplied by s. So I need to distribute. So this becomes sx and yx. So let's do that. Oh, maybe I'll just type n minus, I don't need your help, n minus, and then I have a parentheses, becomes sx plus yx. Oh yeah, I like that way better than my stylus. Let's do that. All right, so I end up with n minus x sx and plus yx. And now what do I have to do? Well, now just like I did in the last problem, just like I did in the last program, I have to distribute out this negative number, right? So I end up with n minus, thank you, n minus sx, but also minus yx, because I had to because I had to distribute this negative number here, because this is n minus this whole thing, so n minus sx minus yx. Thanks for bearing with me. This is the first time I've used this this procedure in showing math on the internet, so I'm excited to show this to you. Back in time a little bit. Okay, yeah, no, all right. There we go. All right. And so here we have this next one. Now this one looks scary, but it's not, right? We've got xy and then times 2 minus n squared. And you're like, oh no, foiling, I want to die, right? Yeah, no, we're not going to foil in this class. But what I do want you to recognize is how to do it. You know, front, outer, inner, last, right? How you would approach a problem like this, right? How first you would. First, you would take n minus, you would essentially go like this. You would have xy out here, sure. But then you would have 2 minus n in parentheses. And because you're taking 2 minus n squared, that's the same thing as going like this, right? And you would put parentheses around this whole thing to show that you do this first. Right? This is how you would approach a problem like this. And so the first thing I would do is I would do first. I would have with a 4. Then I go outer to, let's see, oh, whoops, n. That's a mistake, n. So 2 times 2 is 4. Then I do outer 2 times negative n, so minus 2n. Then inner, negative n times positive 2, negative 2n. And then last, negative n times negative n would, of course, be a positive n squared. Right? But I still have this xy left over, right? I have this xy left over that was on the outside of all of this, right? Oh, what happened here? N squared. N squared. There we go. Right? So here, what is that there? There we go. So I have xy times 4 minus negative 2, minus negative 2n minus negative 2n plus positive n squared. So I combine these like terms, right? Because these are not n squares, these are just n's. End up with negative, what is it? Negative 4n, because we're combining like terms. And now all I have to do is distribute out this xy. 4 times xy, negative 4n times xy, and positive n squared times xy, which, if you look up here, is exactly what I have, right? I just distributed out the xy into the terms. Now again, are we going to do a ton of foiling this semester? Absolutely not. And if I was teaching you algebra, I would take this much more step by step. I'd be showing you every single step over and over and over again. We'd go through a million different problems like this. But this is the kind of skills I assume you already have walking into this class. And so if these skills feel kind of rusty to you, make sure you try to brush off those cobwebs before attempting this class. All right, moving on. All right, so an equation like this is essentially solving for x. And I've already given you the answer here, right? Or excuse me, getting x by itself. Getting x by itself. How do you get x by itself is how you approach a problem like this, right? So how would I approach this problem? Well, the first thing I would do is I would get rid of this negative x. Yep, I would just want to get rid of it altogether. And since it's being subtracted over here, how I would get rid of it is by adding it over here. But anything you do to one side of the equation, to refresh your memory, you have to do to the right side of the equation. So if I'm going to add 6 over here, I need to add 6 over here. And then I end up with the expression 3x equals 18. Well, now what do? Well, now I have to I'm trying to get x by itself, so I'm going to essentially divide both sides by 3, right? So I'm going to take 3x and I'm going to divide by, 3. And I'm going to take 18 and I'm going to divide by 3. So I take 3x divided by 3, and then I take 18 and I divide by 3. And so 3x divided by 3 is just, what is it? It's just x, right? Because then the 3's cancel each other out. And so then you end up with things that I don't want underlined. You end up with x equals, well, what do we have to do? 18 divided by 3 is 6. So in this case, x equals 6. Go back in time so we can do the next one. Right? X equals 6. All right, so now how do I approach this problem? 4x divided by 4. Well, you might remember that anything on the top of a fraction, if it's in the bottom of the fraction too, barring things like parentheses that complicate your life, you can just cancel them out. And so the 4 cancels out the 4 to just arrive at 8. So, how to get x by itself when there are no numbers, right? Once again, it's important to know how to approach problems like this that only have symbols, right? So how am I going to get x by itself in a problem like this? And of course, here's the answer, but let me walk you through. So here's the answer, telling you what the answer is. So let's figure out how I solved this. So first thing I'm going to do is I'm going to try to get rid of this y. So I'm going to add y to both sides, because since this is a negative y over here, if I add y to both sides, that y is going to disappear from the side with the x. And the whole goal here is to get x all by itself, right? So I take s on the left-hand side, and I add y. And then I have what's left over is nx, right? Well, I want x all by itself because I'm trying to define x, solve for x. And so the way to get x by itself here, because I'm multiplying x by n, I can divide, right? I can take this and I can divide this by n. I can divide this by n, and then n will cancel out n, and I'll have x left over. And what would that leave me with? But what do I have to do then? I also have to divide s plus y by n. And so then the final answer is x equals s plus y over n. Now, how do I solve this problem? Oops. So I have z equals x plus y over s. Now I go ahead and tell you that this is the answer, that it's x equals ss minus y, but let's see how I got at that. Let's delete that for now. How am I going to get at an answer like this? Well, the first thing I would do is I would get rid of this s down here, right? Because both x and y are in the upper part of the fraction, and so I can't just get rid of y yet. First, I'm going to have to get rid of my fraction in order to deal with the y and get rid of the y. So since I'm dividing by s over here, if I multiply the top part of the fraction by s, then the s's will cancel each other out. Well, then I have to multiply the left-hand side of the equation, z, by s as well. And so what I end up having is this. I end up with z times s, whoops, not z, Z times S equals X plus Y, right? Not supposed to be a capital. Z times S now equals X plus Y. Well, how am I going to get rid of this Y? Since I'm adding it on this side, I can subtract it on this side, subtract it on this side, and now voila, I'm going to have X all by itself. So just to make it clear, I am subtracting Y from this side, which makes it go away. Subtracting Y from this side, which makes it go away. But then I also have to subtract it from this side. And then I can just get rid of the parentheses. They're not necessary at this point. Ta-da! And of course, this expression is the same as the right answer I showed you at the beginning. All right. So that is all the math I expect you to have walking into this class. If you can do all those, or all of those felt super, super, super familiar, and you're like, yeah, I could totally sit down and figure out how to do those. Because again, that's the kind of math I assume you have walking in, right? I'm not trying to teach you that math. I'm trying to just refresh your memory of what I hope you have already learned in another class. But now on this slide, this is actually what's called summation notation. And it's actually not a math that I assume you've had before walking into this class. And all summation notation is taking the Greek letter sigma, this funny looking, this is not an E. It's not even the Greek letter that corresponds to E. It's actually the Greek letter that corresponds to S. It's the Greek letter sigma. It's right here. It is what's called a mathematical operator. It doesn't, much like the multiplication symbol is a mathematical operator, right? Let me show you so this is the multiplication symbol. It's a mathematical operator. Here's the plus sign. It's a mathematical operator. Here's the equal sign. It's a mathematical operator. Here is the minus sign. It's a mathematical operator. It's a symbol that tells you to do something. Does that make sense? I hope it does. The uppercase Greek letter sigma, this one right here, is also a mathematical operator. It doesn't represent a particular number. Rather, it tells you to do something. And it tells you to do something to anything to the right of it. Anything to the right of it. So see this symbol here? X sub I. X sub I. That's how you say this symbol here. X sub I. Let me, I'll go ahead and write that for you. Here is what I mean when I say X sub I. X sub I. This symbol right here is X sub I. And that is in fact a symbol that represents a number. It's a symbol that represents a number. And the number that it represents is actually a series of numbers. So up here, you see I have this little data set. This is called a data set. And I'm telling you that X equals not just one thing, but 5, 6, and 1. Let's say this is the number of children people have in this class. One person has 5 children, another person has 6 children, and the last person has 1 child. Or let's say this is the number of pairs of shoes people own. And the first person owns 5 pairs of shoes, the next person owns 6 pairs of shoes, and the last person owns 1 pair of shoes, right? This X then represents not just one number, but all 3 of these numbers. And so then this X sub I, this number right here, this X sub I right here stands for 5. It also stands for 6, and it also stands for 1. This whole thing here, X sub I, stands for all 3 of these numbers. Now, so then what does the I stand for? Well, I like to think of the I in this X. I like to think of this I that is the subscript. That's what we call this I. We call it a subscript. I like to think of it as standing for individual human person. Let's say the X stands for the number of kids that you have, or the number of shoes that you have. In this example, I'm just making this up, right? 5 could stand for the number of pets that you have. Let's say somebody has 5 fish, and this person has 6 dogs, and this person has, 1 cat. Whatever it is, X stands for all of the numbers, and this is telling you, by the way, X for this individual person, and X for this individual person, and X for this individual person. So X of I stands for each and every single one of these numbers. This is called a series of numbers. Similarly over here we have Y, and let's say this is the number of caffeinated beverages somebody drinks. So Y represents the number of caffeinated beverages that somebody drinks. So the first person, the first individual human person, drank 3 cups of coffee. This next person, this next individual human person, drank 2 cups of coffee. And then this last individual human person drank 4 Red Bulls. So this Y sub I here stands for Y, which stands for the number of caffeinated beverages. And then I tells you individual person 1, individual person 2, individual person 3. So that is what these symbols represent. They represent a series of numbers. Now, let's go back to sigma. What does this sigma represent? This sigma tells you to do stuff to all of these numbers. Because remember, this X sub I stands for all 3 of these numbers. This Y sub I stands for all 3 of these numbers. So this sigma tells you I equals 1, so start at the first person. Individual person number 1. The person who said I own 5 pets is individual person number 1. That's what this I equals 1 means. 3 up here tells you to count 3 people in and do all of the people until you get to the third person. Now that's all the people. And in this class, we're always going to be using sigma with all of the people. Always. And so instead of 3 up here, you might see the symbol N. Big Mama N is what I like to call it. It's the uppercase letter N, and that just tells you do it to all the numbers. Do it to all the numbers. But it is a general mathematical operator, and you just essentially put up here the number of numbers you're supposed to do something to. Now, what are you supposed to do? Well, this uppercase Greek letter sigma tells you to add. That's right, this funky thing here that looks so confusing and scary, it's a fancy way to tell you to add things up. So X sub I is 5, it's also 6, and it's also 1. So what this uppercase Greek letter sigma is telling you to do this uppercase Greek letter sigma, what it's telling you to do is essentially add up 5, 6, and 1. That is what it is telling you to do. So it's telling you this uppercase Greek letter sigma right here. Oh, I've got all this weird yellow on my thing. Hold on, let me erase all that yellow. Okay. This uppercase Greek letter sigma looks like a funky E. It's not a funky E, but let's, it's not a funky E. The uppercase Greek letter sigma is telling you to take 5 and add it to 6 and then add it to 1. And what is 5 plus 6 plus 1? Well, 5 plus 6 plus 1 is 12. And now you're thinking to yourself, well, why didn't I just write 5 plus 6 plus 1? Why do I need this crazy thing called the uppercase Greek letter sigma, which is a fancy way to add things up? Well, imagine you had 100 numbers. 100 numbers, all in a big Excel file. Or let's say you had 1,000 numbers, all in a big Excel file. And you're like, I don't want to have to type out 5 plus 6 plus 1 plus 7 plus 3 plus 4 plus 6 plus 10 plus 111. I'm just going to say sigma x, which means add them all up. It's just a really efficient way of dealing with lots and lots and lots of numbers. And in this class, what we're going to learn is we're dealing with information that comes from lots and lots and lots of different people. And so we're dealing with 100 different people and how many pets they own, 100 different people and how many basketball games they watched last year, or 1,000 people and how fast they drive down the freeway on any given day, right? We're gathering information from thousands of people or hundreds of people. And so we need an efficient way to symbolize all of the people's scores. And the efficient way to symbolize all their scores is to call it x sub I For one human characteristic, like how many pets do you own, or Y sub I to stand for how many caffeinated beverages do you drink, and so on and so forth. And in this class, we're going to be adding things up a lot. And so this sigma, called summation notation, is a fancy way to say add those numbers up. So in this case, sigma x is just 5 plus 6 plus 1, which is 12. Here, it gets a little more complicated, a little bit more complicated. So let's look at why this is just a little bit more complicated, because you see how we've got some other things happening here, right? It's not just add up all the y's. What this is saying to do is add them all up as a last step. See, this is a last step. It's got all these parentheses over here. It's saying do all of this to all of the different scores, and then as a very last step, add them all up. And so let's look at how I would do that. So the first person answered 3. So I take this person and I subtract 5, because that's what this equation is telling me to do, right? Take all the y's and subtract 5. But I have 3 different y's. So now I have to not only subtract y from 3, but I have to subtract 5 from 3. I have to subtract 5 from 2. And now I have to subtract 5 from 4. So I take 4 minus 5. And that's the idea. Now, because I have to do the inner parentheses first. So I do the inner parentheses first, and I take this person's y and I subtract 5. I take this person's y and I subtract 5. I take this person's y and I subtract 5. I believe I used the example of caffeinated beverages here, right? And so now I end up with 3 minus 5, which is negative 2. 2 minus 5, which is negative 3. 4 minus 5, which is negative 1. But I'm not done, because this equation over here is telling me to do one additional thing. And what is it telling me to do? It's telling me to square. So I have to take negative 2 squared. Let's see if I can. All right, so this equation is telling me, right, I did 3 minus 5, which was negative 2, but now I have to square it, right? And then I have to do the same thing. And then I end up with negative 2 squared. And what is negative 2 squared? Well, it's negative 2 times negative 2, which is 4. And I have to do the same thing here. And I end up with negative 3 squared, which is 9. And I have to do the same thing here. I take negative 1 squared, which is negative 1 squared, which is 1. Right? And now I've done all of this. I've taken all the y's, this person's y, this person's y. And what does y stand for again? In this case, it stands for caffeinated beverages. How many caffeinated beverages did people drink, right? That's the idea. So first I took this person's y and I subtracted 5. Then I took this person's y and I subtracted 5. Then I took this person's y value and I subtracted 5 to get negative 2, negative 3, and negative 1. And then I squared each and every one. Negative 2 squared, negative 3 squared, negative 1 squared, right? To get 4, 9, and 1. But I'm not done, because here is that summation notation. It's telling me now you got to add them all up. Start at the first person. Start at the first person, I equals 1, and go to the third person, which is everyone. Now again, in our class, we're always just going to be adding up all the numbers. So instead of having a specific number up here, you will often have the letter N. The letter N, like Nancy or Norwood or Nyana, N, like net. The uppercase letter N stands for all the people. How many were there? In this case, N is 3. In this case, N is 3, right? So that's why there's a 3 here. So 1 plus 9 plus 4 is, you guessed it, our answer here, which is 14. All right, summation notation is the only new math that I expect you to have had at this point. And so if this is confusing and you're like, I just didn't understand anything that she had to say, watch this part of the video again. And then if you're still confused, go ahead and shoot me an email, or better yet, post in the Q&A forum. All the other mathematical sort of equations we went over in this video, again, those are the mathematical equations that I have assumed that you've had up to this point. And if you have any constructive feedback about how to make my executing the equations in the slides here, please feel free to also shoot me an email with any suggestions you have. Do you prefer me writing with the stylus? I was writing on there, or do you prefer me typing out the answers? Just shoot me an email, give me some feedback, or if it didn't matter to you, then feel free not to say anything. All right, and I will see you next time where we will talk about data. Hooray! Have a good one.